Hello, class. Okay, we're going to talk about something called the Doppler effect today. And before we talk about what that actually is, let's say we have a source of sound that's producing sound waves that travel, and then over here we have an observer that's going to detect these waves. And imagine you're the observer. You want to know the frequency of the sound that you're observing. How would you determine that? And basically, remember, frequency is the number of cycles per second. And if these are wavefronts, they're separated by a wavelength. So, like, one cycle is just one wavefront passing you, and then the next one. Like the cycle occurs when, like, say, one wavefront passes you, and then another one. That would be like one cycle. Just that interval between the two passages that would complete a cycle. And so, if you wanted to, say, measure the frequency of the sound that you're observing, let's write it down here. We could say the frequency would be the number of cycles over some time period. Like a very convenient time period would be 1 second. So just you could get out your stopwatch or something. 1 second, count how many wavefronts pass by, and that would be the frequency. Now, the Doppler effect is when, let's just say that the source and the observer are both at rest with respect to the air, because the sound waves are moving through the air. So let's say the source and observer are at rest with respect to the air. Then the frequency that the observer detects would be the frequency of the source. I guess another way, like say we have a speaker, it has this membrane that oscillates back and forth, and if you just have it going in a pure tone, it's just oscillating like a certain number. You can look at the vibration of that membrane to define the frequency, and that's what the observer would see. However, what if the source is moving towards the observer? Or let's say, what if the observer is moving towards the source? So if we look at it like a stationary observer, we can picture there's these wavefronts. Remember, these wavefronts are moving with a speed v, which is the speed of sound, which we're going to take as our standard value, 343 meters per second. So a stationary observer, in 1 second, they're just sitting here waiting for these wavefronts to catch up to them and just count the number. But if the observer is moving, they're going to maybe catch some extra wavefronts, because in that time, in that time interval, they might just, because of their motion, they might catch some extra ones, and so they'll observe a higher frequency than what the source is actually producing. And similarly, if the source is moving towards the observer, we can also see a higher frequency. However, the two cases are actually different. And you might be thinking, shouldn't they be the same just by the principle of relative motion? Source moving towards the observer, that should be the same thing as the observer moving towards the source. But not in this case. And the reason why is because there is a third reference frame here, and that is the air itself. And we're going to see that a source moving through the air has different effects than the observer moving through the air. So remember, the speed of a wave depends on the medium itself. So like once these waves are created, they're going to be moving at the speed of sound through the air. So if the source is moving, that's going to cause the frequency to be affected. And similarly, if the observer is moving, but the effects are different, so we're going to consider them one at a time. First, we're going to consider a moving source. So I'm going to draw a slightly different picture here. Actually, I'm going to first draw beneath and then I'm going to erase this. Let's say we see wave fronts that look like, or you know what, let me erase this dot in the middle. Say we see wave fronts that look like this. And again, if you could visualize wave fronts, if you could take a picture and actually see them, this is what they would look like at one moment in time. But they're moving radially outwards. And what we can say about this is that both of these circles are centered at the same point, and this means that this wave, the source of these waves is not moving. How do we know that? Well, let's look at this wavefront was created earlier. Let's say that this wavefront was created at time t equals 0. Now, maybe the source, and again, if we see this wavefront, we know that at t equals 0, the source was right here, because it moves away from the source uniformly, goes the same speed in all directions. Now, maybe, again, it was created when the source was here, but it's spread out a certain distance, and maybe when you see this wavefront, a certain amount of time has passed from when the wavefront was created. Remember, it started out small, and it grew to this size. So maybe in the time it took this wavefront to grow, maybe the source moved. Now, if it moved over to the, let's say it moved to the right, what would the picture look like then? Well, we know at t equals 0, the source was here, right in the middle. However, it's moving to the right. Now, one period later, we'd have a new, let's say that the new source, and at time delta t equals 1 period. So remember, the wavefronts are separated by 1 period in time. We have to go through a complete cycle to create another one. So let's say that after a time equal to 1 period, the next wavefront is going to be centered, or the source moved this distance, and so it's going to be centered on this point. And so, I'm not terribly happy with this picture. Let me redraw. So this is where the source was at t equals 0. And then let's say at t equals 1 period, the new source is here. And actually, I can't draw this picture. This one's acceptable at least. This would be an object that's moving fairly quickly. And we'll call the speed Vs, where the speed of the source would be this distance traveled, let's call this distance d, times the period. So that's times that time interval, but again, we're looking at the creation of two wavefronts, so that time interval is 1 period. And so if you're the observer over here, the source is moving towards you, and you're going to see these wavefronts much more, well, I don't want to say much, according to this picture, they're much more closely stacked together than they would be if the source of sound was stationary. Whereas if you're on this side, the source is moving away from you, and the wavefronts are more, they're spaced further apart than if the source was stationary. And so what you're going to see, this observer is going to see a shorter wavelength, and this observer is going to see a longer wavelength. Remember, the frequency and wavelength are related by the speed of sound. And so if you see different wavelengths, the speed of sound is the same, you're going to see different frequencies. So I'm going to erase this picture and just draw a more compact version for a different perspective as well. Let's say these are our wavefronts. It's hard to draw this in an accurate way. So here, this first wave we're looking at that started at t equals 0, that's at the center. And then a time capital T later, the next one is centered here. And so we can say that this distance is Vs. Sorry, I totally wrote this wrong. Sorry about that. Distance is Vs times the period. Okay, so here the distance is Vs times the period. Now, let's say lambda is a wavelength that a stationary observer would see. Or I'm sorry, what a stationary observer would see if the source was also stationary. And let's say lambda prime is what the observer over here is actually going to observe. And so I wrote down the equation. Lambda prime, this is what the observer sees. This is what the observer would see if the source was stationary. And this is how much the wavelength was reduced. You know, the whole pattern shifted, like the second wavefront was shifted a distance d towards the observer. And so the spacing between them was reduced by that amount. And so we can say that lambda prime is equal to lambda minus the velocity of the source times the period. Okay, now looking at this equation, lambda prime, that would be the speed of sound. V is always the speed of sound. This is a wavelength that the observer is going to actually see, and so that's going to be related to the frequency that the observer sees. Now, lambda is what we'd get with no relative motion, so that would be V divided by the frequency of the source. If the source was not moving, then yeah, we would just see it, the sound waves produced like at the same frequency as the source is actually producing. And then we have minus Vs times a period. And remember, frequency and period are related. Frequency is 1 over the period, or the period is 1 over the frequency. And we want to use frequency of the source here, because we're looking at it from this perspective here. Forget the observer. You know, in one period it moved over that distance, and that's where that d came from. And so yeah, in a sense we're done. We have something. Let's say we know the speed of sound, we know the speed of the source, and then we have an equation. Let's say we know the frequency of the source, and here's the frequency that the observer is going to see. This is what we want to have. And in a sense, we've done that. We have an equation where this is our only unknown. But let's take the reciprocals and just solve for FO, frequency that the observer sees. So FO over V would equal Fs over V minus, let me be a little careful. Let's not do this yet. Let's say V over FO equals V minus Vs over Fs. Now let's take reciprocals. It would work fine the other way as well, but and then if we multiply by V, all right, I'm going to write it this way. So if we multiply by V, there in a sense, we're done. However, the equation in the book looks a little bit differently. What they did is multiply the top and bottom by 1 over V. And let's write down our final answer. I'm going to wind up changing this later a little bit, but so on top we just have 1. And on the bottom, V times 1 over V is 1. Okay, so that's the form the book would have it in. So why don't we do that last step just so we can write it in the same way. So this fraction on the right is dimensionless. We have Vs over V. Those are both going to be in the same units. So yeah, we just have a number. Oh, one more thing. I'm going to change this to a plus or minus. Because what if the observer's over here? So the source is moving away from the observer. Well, then the wavelength would increase. And so all you would do is replace minus with plus everywhere. And so we can write the general result with a plus or minus sign. And again, you just have to know which one to use. Whether or not the source is moving towards the observer, or the observer is moving towards or away from the observer. That's all we need to know. And again, I'll talk about how we get the right plus or minus sign later. Okay. Now, so that's the case with a moving source. Now we want to consider the case with a moving observer. Okay. Now, I'm going to draw 3 pictures. We have a moving observer. Yeah, I want to draw 3 pictures here. First, let's say this is observer at rest. So what we have here is, and we're going to consider a stationary source. So we have the source that is sending out wavefronts. And we have a stationary observer. And the frequency that the observer sees would just be the number of wavefronts. I mean, just, yeah, we have it right there. The number of wavefronts in whatever time period. Now, let's look at a simple example. Let's say it just happens, we pick the right frequency, so that, or this is, V is just the speed of sound. So let's just say we can make a tuning fork with a frequency of, say, 1 over 343 hertz. And so, or I'm sorry, do we want that? No, let's say the frequency is 343 hertz, then the wavelength would be 1 meter. So we could set that up. And so the spacing between each wavefront would be, just for convenience, we can say it's 1 meter. And let's say in some time interval, this whole pattern shifts 10 meters to the right. How many wavefronts would cross us? It would just be 10. They're each 1 meter. The whole thing moves 10 meters. We're going to count 10 wavefronts crossing us. Now, in general, the number of wavefronts that we're going to see would be the distance that this pattern traveled, which would be the speed of sound times whatever time interval we picked, divided by the wavelength. So the number we would see, this is the distance that the whole pattern traveled. So again, if we just say the wavelength is 1 meter, if the distance is 10 meters, then we divide by the wavelength, we count 10 wavefronts. If the distance was, say, half of a meter, we'd see twice as many. They're twice as closely packed together. So if they travel the same distance in that same time period, but then we divide by the wavelength, which would be half of a meter, and dividing by half is multiplying by 2. And we can see that the delta t cancels out here, and so we just get v over lambda. Again, just if we multiply by lambda, we get speed is frequency times wavelength. Okay. Now, I want to look at this from two different additional reference frames. Let's call this a ground frame. So we're looking at a stationary source that's sending out these wavefronts that are moving a velocity v, and again, they have a wavelength between them. But now, let's say the observer is moving towards the source with a velocity VO for velocity of the observer. Now remember, the way that we determine the frequency is by counting the number of wavefronts that cross us. So I'm going to shift reference frames here. Let's look at this from the observer frame. So in that case, say you're running along with the observer is now at rest in this frame. But these wavefronts are not moving with a velocity. They're still separated by the wavelength. But now the speed that these wavefronts would appear to approach the observer would be v naught plus v. So again, it's like, let's look at a simple example. Let's just say like there's a car driving. Let's say 10 meters per second. And say you're running towards the car at a velocity of 5 meters per second. Now, from your point of view, you are at rest and the car is moving towards you. How fast does a car appear to be moving towards you? 15 meters per second. Like, if you wait 1 second, the car moved 10 meters, person moved 5 meters. They're getting closer by a distance of 15 meters in 1 second. So the relative velocity would be 15 meters per second. We just add them. We could work this out with all the subscript notation, but I think this is intuitively good enough. So because they're coming closer together, we just add the velocities. So now from this observer's point of view, the frequency that the observer is going to see, just like before, the number of wavefronts they see in whatever time interval we pick, well, the number of wavefronts that we see would be, they're moving with this velocity, v plus VO for observer. So again, we're just doing the number of wavefronts would be the distance this whole pattern moved towards the observer divided by the wavelength. So this whole pattern, remember we're looking at the observer at rest, and these wavefronts are moving towards the observer at this speed. So the whole pattern is going to move this distance in that time delta t. So again, the number we would divide by the wavelength. And then because we have delta t in the bottom, that cancels out. So what we have is v plus v0 times lambda. Or v times lambda plus VO times lambda. So now we just want to convert everything to frequencies. Actually, maybe we should leave it. Yeah, let's not distribute this yet. The wavelength would be the frequency of the source divided by the speed of sound. So now, actually, we're kind of done here. Let's just clean this up a little bit. Frequency that the observer sees is going to be the frequency of the source times this fraction. And just like before, we're going to multiply by 1 over v over 1 over v. So we have the frequency of the source times 1 plus VO over V divided by 1. So we don't need to write that as a fraction at all. So that's our final result. If we have a moving observer, stationary source, moving observer. Oh, and again, if we were moving away from the source, then we would replace V by V minus V naught. And so again, it would just carry through everywhere. We'd have 1 plus or minus V naught over V. Now that raises a question, what if both the source and the observer are moving relative to the air? Well, then you'd have both of these going up. So basically we'd have this factor, which had a 1 there, but we can ignore that, to take into account the motion of the source. And again, we have the same frequency of the source. This is the correction here due to the motion of the observer. So we can just replace this. And this is our final formula. Frequency observed is equal to the frequency of the source times 1 plus or minus VO over V divided by 1 plus or minus Vs over V. So in looking at this formula, there's a couple things we need to know. First off, what do all these letters mean? So O stands for observer, S stands for source, and V by itself is the speed of sound. It happens to start with the same letter as source. Sound and source, so we don't want to use the same, we had to pick. So we just leave V to be the speed of sound. And the other thing you need to know is how to pick the right plus or minus sign. And so I want to talk about that. Now I think the book writes this formula a tiny bit differently, where I think they have 1 plus or minus, and on the bottom they have minus over plus. Yeah, they have a convention for dealing with this, but it's I'm tempted to say it's kind of stupid to have a convention for something like this. Like you have to consider like all the different cases, and no one's going to remember any of that. So the idea is, let's just look at an example. Let's say that the source is moving to the right, and the observer is moving to the left. So the frequency that the observer sees. So all we have to do is pick the right plus or minus sign for each one. Okay, so here's our formula. So let's just consider each one individually. Let's consider the motion of the observer first. That's actually the easier one. So the observer is moving towards the source. Now, what effect should that have on the observed frequency? Well, obviously, it's going to increase the frequency. If you're moving towards the source, you're going to see more wavefronts in a given time period than someone that wasn't moving towards the source. Yeah, we can look at a different reference frame. We can look at like an error frame. I think that's what I actually did in the notes. Where we'd have, say from that perspective, the observer plus the speed of sound. You know, if you're moving, you're going to travel a greater distance in any given time interval, and so you'll just catch more wavefronts. So yeah, I think I did that in the notes. Instead of the frame where the observer is at rest and the sound waves are moving towards the observer, I think I did where the sound wavefronts were at rest, but the observer was moving. It's different ways of doing the same thing. But this way you can picture it like you're just like running through these stationary targets, and the faster you're running, the more you're going to see in a given time period. So if you're moving towards the source, the frequency has to increase. So obviously we would pick the plus sign there. Now the source is moving towards the observer. That's also, remember, when the source is moving towards the observer, the wavefronts build up. They're closer together. So if the wavelength is shorter, that means the frequency is higher. And so we should observe an increased frequency due to the motion of the source. And this one's a little tricky. Because it's in the denominator, we'd want to use a minus sign here. Because that's kind of why I like the way the book does it, with 1 plus a minus, and then 1 minus, plus or minus that. Because if we pick the plus sign here, then we'd be dividing by something bigger than 1, which would make this number smaller. So if we pick a minus sign, it's easy to see from the denominator. With a minus sign, we're going to be dividing by something that is less than 1, and that'll make the frequency larger. So, yeah, you just have to be very careful about picking signs. And just remember, if you're moving closer to the source, frequency increases. If you're moving far, you don't really have to remember that. Just think about it, and you can figure out the right, is a frequency going to increase or decrease because of this motion? And then you can just be careful picking the signs to make sure that that happens. Now I should point out one other thing. We could, what if we have this ridiculous example where the source is moving, say, at the speed of sound? Then Vs divided by V is 1, and we're dividing by 0. So obviously that's a problem. And again, this formula only works if we're moving less than the speed of sound. Again, the sound waves, the faster you move, the more closely packed these sound waves get towards each other. Remember, these are compression waves. They're high pressure. When you cram a lot of them together, the pressure builds up, and that's why you get this sonic boom. When the plane breaks through that barrier, it creates a sonic boom. Apparently, Chuck Yeager, he was the first. I think he was the first person, definitely the first American, to exceed the speed of sound. And if I remember right, I think I read this or saw it in a movie or something. People on the ground heard the sonic boom and thought his plane blew up, but no, that was him crossing the sound barrier. At one point, they thought that was impossible because the pressure would build up so much that it would destroy anything trying to pass through it. But anyways, our formula only works if we're moving less than the speed of sound, which is typically the case. Okay, so we'll do some examples during the review. And yeah, that'll be it for the Doppler effect.